today I gave you a warm-up as a bit wordy. You and your friend really like ice cream, especially 3-scoop ice cream cones. I just want ice cream. Your friend really only likes chocolate, vanilla, and strawberry. But in a cone, you can arrange the flavors in different orders for a completely new taste experience. I know. I might not have written it, but I can be dramatic with it. How many different 3-scoop cones can be made with the flavors if you do not double up a flavor? Well, what orders can I do? Give me an option. Caleb, you're up first. What is one option for this ice cream cone? He likes all 3. Okay, we can go chocolate, strawberry, vanilla. That's one option. Andrew, what's another option? Perfect. That's another option. Julia, what's another option? Beautiful. Quinn, what's another option?
Vanilla and strawberry chocolate.
Beautiful. Dominic, I'll come back to you after you've been in the class for more than a half a second. Kale, what's another option?
Chocolate, vanilla, strawberry.
Cade, what's another option?
Strawberry, chocolate, vanilla.
Sarah, what's another option? Or are we out of options? We're out of options. How many different ice cream cones are possible? 6. Is this the only way to do this? This is the only option that I have to list out all possible flavors. I hope not, right? If my only option is to list out all the flavors, then when we get to question 2, where there are 31 possible flavors, we're going to be here for a while. So, let's think of another way. So if I got my little ice cream cone, I try to put the first scoop on there. How many different options do I have for the first scoop? 3. Now, if I've put a scoop on there, whether it be chocolate, strawberry, or vanilla, how many options do I have left for the second scoop? Only 2. Because I've used one of the flavors, and the rule is that we like all 3. How many options do we have for the last one? 1. Which means, in probability, we have something known as the counting principle that says the number of options you have for the first thing times the number of options you have for the second thing times the number for the third thing, and if you keep going, you just keep going. Multiply them all together, that gives you total number of options. Would you agree with me that 3 times 2 times 1 is 6? Now there's another way of writing 3 times 2 times 1. Exclamation point being in there, sound familiar? It's known as a factorial in mathematics. It means to multiply a number by every number smaller than it, all the way down to 1. So, factorial is coming back. not the only way to do it. Factorials relate us to something that you would have done in advanced algebra, combinations and permutations. Do we remember hearing about combinations and permutations? I'm getting some yeses. I'm also getting some people like, no. Fair. Now, those of you who remember hearing about it, do you remember the difference between a combination and a permutation? No? Okay, we'll come back to it. We'll come back to it. Okay, now that was your friend who is a very bland in their ice cream choices of chocolate, vanilla, and strawberry. You, on the other hand, are more adventurous with your ice cream. Baskin-Robbins Ice Cream Shop offers 31 flavors for your enjoyment, and you are open to all of them. How many different 3-scoop cones can be made with the flavors if you don't double up the flavor? Now, we can go through and do the listing if we really want. We'd spend most of the class probably trying to come up with the list of all the different options if we manage to make it. Let's try another way. Let's try the counting principles. For the first scoop, how many options do I have? 31. Times, I don't double up a flavor, so how many options do I have for the second scoop? Third scoop? 29. What is 31 times 30 times 29? Yes, I have the answer. Yes, I expect you to come up with it. If you don't have a calculator, I'd probably grab one unless you're doing all that math in your head. 26,970. Did we want to list out this number of cones?
No.
Probably not. We'd be here for probably more than a class period trying to get them all. Is this fitting the factorial idea? For the first problem, it was 3 factorial because there was 3 possible options. Is this 31 factorial? No. Does it look like the beginning of 31 factorial? But then all of a sudden it truncates. It stops. It's almost like the 28 down disappeared. How do things disappear if there was multiply? How do you get rid of multiply? Divide. So this is almost as if we had 31 factorial and it got divided by 28 factorial. Because the 28 factorial would have been the 28 times 27 times 26 times 20. You get the point. That 31 factorial should have had it not stopped at 29. Okay. Where do you think the 28 came from? Yes, but had I not written out 31 times 30 times 29, how would we have come up with it being 28? The only thing I knew is there was 31 flavors and I want 3 of them. Minus? Okay, there we go. So it's almost like I have this 31 factorial over 31 minus 3 factorial going on. It almost had this situation where there were n flavors and I wanted R in the cone, and it would have been like n factorial over n minus r factorial. which is the formula. Oops, why did I write a C? P-R. It's the formula for permutations. A permutation, which we will write down here shortly. A permutation is how you choose a smaller group of items from a group where order matters. We had the group of 31 flavors. We chose 3 of them. And because it's an ice cream cone and it makes a completely different flavor experience, order mattered in which one went first, which one went second, which one went third. This one here technically could have been a permutation as well. The only difference is when we had the 3 factorial, had I done my n and my r, it would have been like 3 permutations of 3 and plug into that formula, 3 factorial over 3 minus 3 factorial. 3 minus 3 is 0. And 0 factorial we'll talk about is defined to be 1. Hence it turns into 3 factorial because 3 factorial divided by 1 is still 3 factorial. Second part of what we're talking about. The next time you go out to get ice cream, you go to a shop that only has bowls. That's sad. Your friend still only likes chocolate, strawberry, and vanilla. They are still a very bland ice cream person. However, in a bowl, the ice cream, does the flavor that you scoop them into the bowl really matter? Does that change how you eat it? Or do you get to choose which one you eat first? Does order matter? No, in a bowl, if they put chocolate and vanilla and strawberry, I can eat it in whatever order I want. It is not a different flavor experience, at least in the scooping. If they only like chocolate, strawberry, and vanilla, and they want 3 different flavors, how many different options do they have to get? 1. It's a very sad situation. They've got 1 option only. Expand your horizons. Now you, on the other hand, go to this place, and keep in mind, it's still only got bowls. They are like Baskin-Robbins. They've got 31 flavors. Don't worry, copyright lawsuits already in play. How many different scoop bowls can you make of 31 flavors? So, it's a bowl. Order does not matter. And if order does not matter, it is not a permutation. It's a combination. Combinations essentially take a permutation and divide out the different ways you can arrange things. So, it starts with our permutation formula. N factorial over n minus r factorial, but then it divides something else out. Divides out the number of different ways you can arrange the things that you have. Now, in our situation, we are talking about having 31 items and doing a combination of 3 of them. So we'd have 31 factorial over 31 minus 3 factorial. And now we've got that piece that needs to also divide out. And since there's already something in the denominator, I'm going to multiply by this thing. Now that thing that I divide out, again, is the number of different ways you can arrange the things that you have. If I have 3 items, and I want to get rid of how many different arrangements of 3 items I have, how many different ways can you put 3 items in different orders? Hint, we've already done the math. 6. We did that way back at step 1. We only had 3 items. We figured out all the different orders, which means When I get rid of all the different orders, I need to divide this by that 6, which came from the 3 factorial. Where did the 3 come from? It was R. This is the formula for combinations. So, 31 factorial over 28 factorial times 3 factorial. Now you can go through and you could do the multiply out if you really want. Or you can take into account that when you do 31 factorial, it's 31 times 30 times 29 times 28 times 27, etc. And when you do 28 factorial, it's 28 times 27 times 26 times, etc. And when you do 3 factorial, it's times 3 times 2 times 1. That one's easy, because that one's smaller. Much like we talked about with this one, when we came up with the permutations, isn't a bunch of stuff going to cross out? 28, 27, 26, 25, 24, 23, 22, 21. Everything of the 28 factorial is going to disappear. You're going to be left with 31 times 30 times 29 over 3 times 2 times 1. $26,970 divided by 6. You, in your expansive love of ice cream, have 4,495 options. Does this look a little bit familiar to something you did in advanced algebra? Okay. So, today let's make sure that we're not just getting a warm-up, that we're getting a strong understanding of what we're doing. Today is part of an introduction to 10.6. Tomorrow is also part of an introduction to 10.6. Focusing in on combinations and permutations. A combination in mathematics is this idea of choosing a group of items out of a larger group where order doesn't matter. Welcome back. We just finished the warm-up. We're getting to the main part of our notes. So, choosing a group of items out of a larger group where order doesn't matter. Now, there's a couple of different typical ways that they write out what combinations are. They will write little n, big C, little r. That's the way that I will most commonly do in here, but it's not the only way. Sometimes they'll do a big C, and in the parentheses they'll do n comma r. And if you continue on with mathematics and end up doing math in college, they do this. Keep in mind, there is no fraction bar. That's what people tend to do with this. They tend to write a fraction bar between the n and the r. There's not a fraction bar there. It's just n above r in parentheses. When you see that, that means combination. Now the formula for a combination is n factorial over n minus r factorial getting multiplied by r factorial. Permutation, same idea. Choosing a group of items out of a larger group where order does matter. Now, in all actuality, permutations are the base idea behind combinations. We kind of saw that a little bit in that warm-up when we kind of derived our formula. N permutations of R, also known as P with the N and the R in the parentheses. It does not have a notation like this one, at least not to the best of my knowledge. And it's a very similar formula, N factorial over N minus R factorial. That additional R factorial in the combinations formula is just to get rid of the different variations of order. Since order matters in permutation, we don't want to get rid of them. Now, before we move on to our examples, I just want to make sure we're good on this too. Factorial. The exclamation point. You're multiplying by all whole numbers smaller down to 1. So if I say 5 factorial, that means 5 times 4 times 3 times 2 times 1, which, based on going through our warm-up, I hope we figured that piece out by now. With factorials, though, you do need to know that by definition, 0 factorial is equal to 1. And when I say by definition, I mean someone came in and said 0 factorial is 1. That is the definition. It's not this definition that I wrote up here. It's they defined 0 factorial to be 1. Otherwise, the math doesn't work out. So, today we're going to get questions like the following. There are 12 horses in a race. How many ways can first, second, and third place finish? In other words, how many different combinations can you get for first, second, and third place of these horses? Now, the questions are not generally going to be a whole lot more in depth than that. In order to approach these problems, you're going to have to ask yourself essentially 3 questions. Combination permutation, what's the large group, what's the small group? Combination or permutation comes out of, does order matter or not? You're running in a race. Do you care if you get first versus second versus third? Yes. Does order matter? Yes. Is that permutation or combination? Permutation. N is the larger group. How many are we choosing from? 12. R is the smaller group, or how many we're choosing? The first 3 places. So I'm going to do 12 permutations of 3. I got options on how to approach this. One, I've got a formula for it. N factorial, in this case 12 factorial, over, in parentheses, n minus r factorial, 12 minus 3 factorial. Now keep in mind that 12 minus 3 factorial is not 12 factorial minus 3 factorial. They are not the same thing. You cannot distribute a factorial. You must do the subtraction and then factorial it. Twelve minus 3 happens to be 9. And when I do this, 12 factorial is 12 times 11 times 10 times 9 times 8 times 7 times, you get the picture, right? And 9 factorial is 9 times 8 times 7 times 6 times, you get the picture there too. When you're doing combinations and permutations, some stuff is always going to cancel out. In this case, what's canceling out? Everything from 9 down. 9, 8, 7, because this is going to go 9, 8, 7, 6, 5, 4, 3, 2, 1. Right, so did that. We're left with 12 times 11 times 10. Twelve times 11 times 10? 1,320. That's how many different ways we can get first through third place in this race. But I can also ask the follow-up question. What is the probability that you guess first and second places correctly? This has taken something out of the problem, and it's also bringing probability involved. So first off, I'm going to focus in on probability. If you want to find the probability of something, what do? Simplify it down a little bit. Let's talk about rolling a die. What is the probability that I roll a 6 on a 6-sided die? 1 out of 6. Where'd the 1 come from? There's one option that fits what I want. Where'd the 6 come from? There's 6 total options that could happen. To find probability, I take the number of ways I can get what I want and divide it by the total number of ways anything can happen. We already have the total number of ways anything can happen. 1,320. We calculated that already. What we need to figure out is how many ways we can guess first place and second place correctly. Now, if you've got a situation where you only have 3 places that you're caring about, and you know what that is, and you know what that is, the only thing you have to worry about filling is third place. That's also combinations of permutations. Now this one is a very, very basic combination and permutation because of the numbers, but it still works that same way. How many horses do I have to choose from to fill the third place slot? There were 12 horses. I filled first and second place already. How many were left over? 10. How many slots do I want to fill?
1.
Left, 1. I'm going to do 10 permutations of 1. 10 factorial over 10 minus 1 factorial. That's 10 factorial over 9 factorial. I could write out 10 times 9 times 8 times 7 times 6, blah, 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 blah. And I could write 9 times 8 times 7 times 6, blah. But what's all going to be left? 10. There are 10 ways that I can guess first and second place correctly. There are 10 ways I can get what I want, but I'm looking for probability out of how many total ways can we do things again? So the probability is 10 out of 1320. I either simplify it down to get 1 out of 132, or I go to my calculator and do the actual division. What's that as a percentage? 0.76%. Or if you prefer to leave it as a decimal, if you're leaving it as a decimal, go to 4 decimal places. If you're changing it into a percent, 2 decimal places after the percentage. If you're leaving it as a fraction, make sure it's simplified. I've just got one more example with a follow-up question for you. There are 26 students in a class, specifically this class today. How many ways can I choose 4 to go down to the Deca store? Does order matter? No. You're just excited you get to go to the Deca store if you get chosen. You don't care if you were first or last. You get to leave class to go to the Deca store. So, order doesn't matter, meaning combination. What's N? 6? 26, okay. R? 4. N is the number you have to choose from. R is the number you're choosing. 26 combinations of 4. Combinations have the n factorial over n minus r factorial, n is 26. 26 minus 4 in parentheses factorial, 4 factorial. Do a little bit of subtraction. I get 22 factorial and 4 factorial. 22 factorial times 4 factorial is not 88 factorial. Do not multiply those. At least not in like 22 times 4 and leave the factorial. Doesn't work that way. Times 25 times 24 times 23 times 22 times dot dot dot. 22 times 21 times 20 times dot 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 times 4 times 3 times 2 times 1. What is going to cancel out? Everything after 22 on top. And on bottom, the 22 factorial. You're going to leave the 4 times 3 times 2 times 1 because the 4, 3, 2, and 1 that were in this 22 factorial, or this 22 down piece, were in the 22 factorial. 26 times 25 times 24 times 23 over 4 times 3 times 2 times 1. Make sure if you're typing it into your calculator, you're doing parentheses, or I just do the numerator and denominator separately. $14,950 ways. Whew. Is there an easier way to do this? Can the calculator do combinations and permutations, in other words? Yes, the calculator can do combinations and permutations. I don't care if you do it in the calculator. Please do, at very least, write out like this piece. Like the what combinations of what or what permutations of what. But if you do it in the calculator, I'm perfectly fine with that. She did. To do it in the calculator, start by typing the first number, 26. In the TI calculators, it is under math. And you've got either 4 or 5 menus depending upon your TI calculator. If you've got the older ones, there's only 4 menus. You want the probability menu. Permutations is second, combinations is third. And then you put the second number. Now, if you've got the newer TI, it puts those numbers literally down there. If you've got the older TI, it will say 26, NCR, 4. That's perfectly okay. On the Casio, it is under option. It gives you a menu across the bottom. You also want the probability menu. Probability menu is not here. F6 will scroll over to find more menus. Probability menu then becomes F3, and there are your permutation and combination. I'm okay if you use the calculator for it. There's a reason I did it by hand at first, because we're going to get to a point where we have to do some of it by hand. That point is not actually today. Okay, I said I had a question and a follow-up. Here's my follow-up question. Now, before I write the follow-up question, for the sake of easy math, and for the sake of easy math only, you have to let me assume that there are 2 genders. I am not saying there are 2 genders. I am not having a debate with you on how many genders there exist. For the sake of easy math, are we okay assuming there's 2, just to make the problem?
Yep.
Okay. If there are 15 boys and 11 girls, what is the probability of choosing 2 and 2? In other words, 2 boys and 2 girls. I can write it out. It's not that big of a deal. Probability, the ways you can do what you want, divided by the total number of ways you can do something. Have we already figured out the total? Yes. We need the ways that fits our situation here. Choosing 2 boys, choosing 2 girls. Still choosing 4, so it's like I have 4 slots to fill. Order doesn't matter, so I'm just going to assume first 2 are boys, second 2 are girls. How do I figure out how many ways to choose those 2 boys? Does order matter? So it's a combination. How many boys are there? 15. How many am I choosing? 2. Girls. Does order matter? Combination. How many girls are there? 11. How many am I choosing? In probability, you have this many ways to do this thing, you have this many ways to do this thing. If I want to figure out the ways to do both, what do I do with those 2 numbers? Add addition. Multiplication. It's the counting principle again. It goes back to what we did in the warm-up. We had 3 flavors. The first option, there was 3 options. The second option, there was 2 options. Then there was 1, and we did 3 times 2 times 1. So, I do 15 combinations of 2. I do 11 combinations of 2. And I multiply them together. I can do them separately, or I can type it all into my calculator in one. If you type it all into your calculator in one, make sure if your calculator puts you down in the base, you get out of it, and you have to do a time symbol, otherwise the calculator doesn't understand. $5,775. Is that the answer I was looking for? No, what do I do with that number? Put it on the top of a fraction because we're looking for a probability. This is the ways I can do what I want. This is the ways that I can do total. I divide them. 5,775 divided by 14,950. There are 3 possible correct ways to give me your answer. What are they? Percent, simplified fraction, or decimals. If I do a simplified fraction, the calculator, I make it do the work for me. 231 over 598. If I do decimal places, how many decimal places do I keep? Just regular decimal? 4. 0.3863. If I change it into a percentage, then 2. Make sure you're rounding appropriately.